Hi, everybody. Today is January 29th, Monday, and we are in ES 2110 statics. We are marching through the material, and today we are going to start talking about chapter 2. But before I do that, I want to take a look at our schedule, which is posted to our Moodle page, and just make sure everybody kind of knows what's going on. On Friday, the January 26th, which was our 5th class period, homework number 1 was due, so submitted through Moodle. I just talked about that a little bit before I started recording. And then we began the videos 4, 5, 6, and 7, 8, and 9, which will cover chapter 2. I think 8 and 9. I don't think 6, 7 are both chapter 2. And then 9, they're all chapter 2. Okay, so basically, if you take a look at our Moodle page, chapter 2 is going to be a lot denser in terms of information than chapter 1. So you can see I have a bunch of stuff hidden. That just means you don't have to look at it. It's not important to this class. But in order to successfully complete chapter 2 and the homework that we're getting ready to, you can take a look at the homework on these 3. I also have some review notes and homework. Sometimes in the past, when I've had students who ask me to work a problem, I'll just do it and post it to the website so that everybody will have access to it. Then you'll start by watching video 4, 5, and then these in-class lectures, which you can look at and just see. Sometimes there's something good on them, so that's why I leave them up. But the numbered lectures are for sure. Make sure that you watch them because those are the content videos. Sometimes I post notes, so just take a look at that. So like while you're looking at, when you're reading about section 2.2, if you look at the lecture notes, that can be helpful. And then more videos, some more homework, and then a problem solving session. A lot of people had, I wouldn't say trouble, but problem 2.2 had some issues that we had to confront. And so I went ahead and worked out that problem. So even though it's a homework problem, or very, very similar to a homework problem, depending on what textbook you're using, if you take a look at that, it will help you a great deal. So then our next homework is going to be due February 5th, which is next week. This Thursday is the 1st, so it must be like Tuesday or something of the next week. Monday or Tuesday. Okay, there you go. So submit your homework here. And then after you get done with that, there's a quiz. Now, I think we've already talked about this, but the quiz will be over chapters 1 and 2. It's open book and it's kind of timed. You have an hour to complete, but it's very important. The way that you complete the problem is very important. So I have steps that I ask you to go through. And the reason I do that is because that's how I want your tests to be written out. And that's how you'll get full credit. Or if you make a mistake, you'll just get the maximum credit based on just an arithmetic mistake or whatever mistake you make. So when you take the quiz, you'll open up the quiz tab, but you'll write it on engineering comp paper and then submit it here through this button. Okay. And I just wanted to make a point of that because a lot of people try to take the quiz here and it really, I've done it in the past, but with homework like this, it's just the stuff we do is individual a little bit, and the quiz, the way it accepts answers is so picky that people lose credit for things they shouldn't lose credit for. So that's why I prefer to handwrite those. Exactly. You got it. Yep. Just do it on engineering comp. Just pull it up here, open it up so you have the work in front of you. You can use your book, you can use notes, whatever. Then when you do your quiz on engineering comp paper and then submit it right here. Absolutely. Yeah. Good question. All right. So like I said, the textbook for chapter 2 is here. And so the next thing we're going to do is to talk about what is the content of chapter 2, since we're going to be working on it for a little bit. But chapter 2 has to do with the statics of particles. So basically, when we talk about the statics of particles, what we are talking about are objects. It's a simplification, but a particle in terms of statics is an object with no shape or size. And what that means is it really can't rotate. It just moves under translating forces. So when this is actually later on, obviously we'll talk about the statics of objects, and then we'll discuss how they rotate and how they, if you push on them in one place, they move differently than if you push on them in the other place. When we talk about particles, we just think about it like this, and that's the easiest way to do it. So the basic formula that we talk about is Newton's laws of motion. And basically, one of those laws says that the forces acting in a particular direction on a mass will result in an acceleration in that same direction. So this becomes important to talk about the difference between acceleration and velocity, okay? Because we always think about in everyday usage, sometimes people talk about acceleration, velocity, or acceleration and speed the same way. And it's definitely not the case. So when we talk about that, acceleration is the change of velocity. So if something is moving at a constant speed in the same direction, it doesn't change acceleration. It's just, it doesn't change velocity, and there is no acceleration. So we start by looking at the fact that velocity and acceleration have magnitude, and they also have a direction. And in general, quantities that have both magnitude and direction are called vectors. Okay, so what that means in terms of a force is if I push downward on this table as hard as I can, it will only produce a force in that direction. And that means that either the force that opposes me will be equal and opposite if it doesn't move, or that the table would go through the floor if I were just extraordinarily strong. But a y-directional force will never produce an x-directional motion. Okay, and similarly, if I push on a table like this, and if I consider this to be x, if I push on an x direction, always moving in the x direction, or oppose, a force will oppose it in the x direction, will never create a motion in a different direction. So when we talk about vectors, then, when we add or do any operations on vectors, we need to take into account the magnitude and the direction. So in other words, let's just say you have a little particle here, and let's say it's being acted on by two different forces. This is complicated, but we'll do the math on something simpler later. This force is going to tend to pull the particle in this direction. This force is going to tend to pull it in this direction. And when we add them together, depending on the magnitude and actual directions of these, the particle is going to move somewhere in between those two in an upward direction. If you have a particle that's being acted upon in a single direction, it will move in that direction. Okay, so when we add, so we talk about vectors, or let's just talk about force. A force then is a vector. And likewise, an acceleration is a vector. Velocity is also a vector. Sometimes when we are talking about how fast something moves, we don't really talk about velocity, we talk about speed. And speed is the magnitude of velocity. So if you say, I was driving 60 miles an hour, the obvious question is, where are you driving to? You know, driving to Billings at 60 miles an hour is way different than driving to Thermopolis at 60 miles an hour. You're going to end up in a different place. But your speed in both cases is 60 miles an hour. All right. So when we talk about forces, we have two different. Well, I don't want to say that. Okay, when we talk about forces and acceleration, if we look at this equation, Newton's law of motion, one of Newton's laws of motion, it's several. We have a force, which is a vector, equal to mass times acceleration, which is a vector. Mass does not have a direction. Mass has magnitude only. And it is called a scalar. Anything that just has a magnitude is a scalar. Now, that also brings up the difference, which we'll talk about very shortly, maybe not today, but within the next week or so, when we talk about weight. There is a difference between weight and mass, okay? Mass is the amount of stuff something has. Weight is how strongly that mass is attracted to a gravitational field. So like on Earth, almost all of the time, weight is a vector directed toward the center of the Earth or downward in the direction of gravity. Mass, on the other hand, is just mass. So if you are an astronaut and you go up into deep space, you go to the moon, and the gravitational acceleration on the moon is 1/6 relative or approximately to what it is on Earth, your weight is 1/6. So if you weighed 150 pounds on Earth, you would weigh 25, you'd weigh a sixth of that, so 25 pounds on the moon. However, your mass, which is not measured in, it can be, it's measured in kilograms in the SI system, measured in something called a slug or a pound of mass in the US system, your mass will not change. So your mass is the same on Earth, in space, on the moon. Weight is not the same. So those are sort of the differences between the two. Mass is a scalar, weight is a vector. So if we have a force, let's just say there's a lot of different directional ideas that we can, and we'll talk about forces, accelerations, vectors in general. But one way that we like to line out forces is using Cartesian coordinates. And Cartesian is just named after the mathematician René Descartes. And he was a French fella a long time ago. So Cartesian coordinates are basically X and Y, or could be X and Z in 2 dimensions, but I try to stay with X and Y. And if you have a third direction coming out of the page, if you're talking about a 3-dimensional force, that force is called Z. So we're going to start with 2-dimensional forces, and we'll expand our conversation to 3-dimensional forces later on. If you have a force and you wish to express it as the vector sum in a couple of different directions, you express it as components in particular directions. Meaning, if we're using Cartesian coordinates, and we have a force of 45 pounds acting at an angle of 35 degrees from the horizontal, we can split this into 2 pieces, an X component and a Y component. And you may notice there's a real similarity between this and a right triangle, because it is in fact a right triangle. In almost every instance, not every single instance, but in almost every instance, when we resolve a force into components, we keep the components perpendicular to each other. And that's because, if you remember, theorem of Pythagoras, x squared plus y squared equals the length or the radius squared, whatever you're looking at. But if they are not perpendicular, you get this minus 2 cosine 2 xy cosine theta term in the middle from the law of cosines. And so when you keep the components perpendicular to each other, it becomes much, much easier to do the math. It's not essential, but it's standard. Okay, so we might ask, what is the component of this 45-pound force in the x direction? The x component is, if you look at this as a right triangle, 45 pounds multiplied by the cosine of 35 degrees. And similarly with y component is equal to 45 pounds. Now we're on the opposite hypotenuse times the sine of 35 degrees. And you can express those numerically by saying, checking to make sure that you're, hang on, I'm making sure you're in degrees. I have a little enunciator right here. Sometimes you can be in grads or radians, which will mess up all of your answers. But if you don't have a good indication on your screen, if you check the cosine of 90 in degrees, it'll be 0. So I just kind of always go to that. When if you try it with a sine of 0 is 0, so it just is 0, so it doesn't matter. But if the cosine is a good way to test that. All right, so my x component here then is going to be the cosine of 35 degrees multiplied by 45, which is 36.9 pounds. Now, once again, that would really be 37 pounds if I'm being close attention to significant figures, but we'll extend it 1 just for right now, just to keep our numbers cleaner. The y component is going to be the sine of 35 degrees multiplied by 45 pounds. And that means that it is 25.8 pounds. Okay, so what that means is that pulling on my particle with a 45-pound force in this direction is exactly the same as if I pulled on it with a 36.9-pound force in the x direction, and at the same time, a second force of 25.8 pounds in the y direction. You also probably notice that 36.9 and 25.8 do not add up to be 45, and that's because they're not in the same direction. So it's a right triangle. If you take the legs of the triangle, the x component, square it, the y component, square it, and that comes out to be the force squared. Let's just check, make sure. So if I take 36.9, square it, and add it to 25.8 squared, I get 2027.25. And so then I need to take the square root of both sides. Where's my, there it is. Second square root, second answer equals F then equals 45.02, roughly 45 pounds. And anytime you do that, unless it's whole numbers, it's going to come out to be irrational. So you're going to have a little bit of extra on the outside. But basically, that is how you break a force into components. Now, you can also add vectors. So in other words, what if you had a 45-pound force acting on something, and then at a different angle, you had a 37-pound force? Okay. Well, the way that you would do that is to add the components. So if you have a vector P and you add it to a vector Q, the way that we would do that is to think about the P component in the x direction plus the Q component in the x direction would be the resultant component in the x direction. And P in the y plus Q in the y would equal R in the y. Okay. And then you could write it in that form as well. But you always want to keep apart the x and the y. You don't add them together after you've broken them into components. We'll talk about how you delineate that later on. All right. Turns out that just like regular addition, vector addition is also commutative, meaning that it doesn't matter the order that you put the vectors in. P plus Q vector, vector P plus vector Q is equal to vector Q plus vector P. There's one thing that I do want to point out. If you take a look at your textbook, when they discuss vectors, they use bold letters. It's very hard to draw a bold letter when you're taking notes. So that's why I put the little vector symbol over it. You can also put like a little cap over it like that. But that's just sort of like a standard method of describing that. Okay. If you have 3 or more vectors, P plus Q plus S, you add 2 of those together and then add them to the third. Vector addition is also associative. So in other words, it doesn't matter which 2 vectors you add together as long as you break them into components first. All right. Now, so now we've talked about breaking vectors into components, and we've mentioned the idea of a resultant, and a resultant vector is the sum of 2 or more vectors. And so if you have a resultant, this is actually how you find a resultant. P plus Q is the resultant of P plus Q. So it's kind of the same thing. Now, when we take a look at why this is important, when we start adding forces together, what we'll find is that sometimes you'll have something that is acted on by more than one force at the same time. And if you want to know how that is going to result, or what the results is going to be on an object, you can find the resultant force. So here's an example problem, problem number 2.5, which I'll work out for you today, and then you'll be set to get started on your homework. We have a stake being pulled out of the ground by 2 ropes. We have 120 Newton force acting in this direction and an unknown magnitude P that is acting in this direction. And we're told that alpha, the angle right here, is 30 degrees. Now it says determine, I'm going to talk about this by trigonometry thing, but I'm just going to work this out and then I'll tell you what is meant by this and what we need to avoid. The magnitude of the force P so that the resultant force exerted on the stake is vertical. Okay, so let me just draw this little stake here. And my 2 forces. Okay, and it says, what is going to be the magnitude of P so that the resultant force is vertical? Well, if I go back to this idea of Cartesian coordinates and I say this is my y direction and this is my x direction, what that means is the x component is equal to 0. If the resultant force is only vertical, it's only y. So what that means is the resultant component in the x direction is equal to 0. Well, how does that happen? Well, that's going to happen when the sum of the 120 Newton force in the x direction plus P in the x direction is equal to 0. Okay, so the first thing I do is I draw, and this is going to be an important technique for you when you are working out problems like this. I have to draw what's called a free body diagram. And I always say a free body diagram is like, well, I used to use this kind of it's all right, I guess. If you think about a human being, what a human being looks like, and then you sort of draw a stick figure that indicates that human being, or maybe if you think it's, I don't know, you think it's a guy, you put a hat on it maybe, right? Okay, this looks nothing like a human being, and yet somewhere in your consciousness, it presents the elements that you say that's a human being. That's what a free body diagram is. A free body diagram is the simplest, only the things we're interested in when we draw this drawing. So we don't really care this is a spike. We just care that it's a point, it's a particle. We don't really care that this is a rope or this is a rope. We just care that they're forces. And then we, of course, care about the angle. All right. So this would be my free body diagram. And what I know that these two things have to equal 0. Well, the one thing I can see about the 120 Newton force is that it moves from the right to the left. The component of that 120 Newton force, because it has a direction, moves from right to left. That means that it's negative. Okay. So if I think about it that way, I can then say that the X component of the 120 Newton force is 120 Newtons. Now this time, this angle is opposite. So that's the sine of 25 degrees. And since it's going right to left, it's negative. So in other words, the X component of the 120 Newton force is negative 120 times the sine of 25 degrees. P in the X direction, on the other hand, is positive because X to the right is positive. So that's going to be equal to P, which is our unknown, times the sine of 30 degrees. And those two things added together equal 0. So I see by my equation that I have one unknown, one equation, and one unknown. So that means algebraically I can solve for P. So the first thing I'm going to do is I'm going to flip this puppy over to the other side of the equation. So I'm going to say P times the sine of 30 degrees equals, when this becomes, it's a negative on the left-hand side, so it becomes positive on the right-hand side. Okay, and then to finish solving for P, I would divide both sides by the sine of 30 degrees. So over here, sine of 30 cancels sine of 30, and I get P, which is what I was after. And then I get P is equal to 120 newtons. And I take the sine of 25 degrees, which is 0.4226, divide it by the sine of 30 degrees, which is 0.5. And if I take 0.4226 and divide it by 0.5, I get a number which is 120 newtons times 0.8452. And then P is equal to those two things multiplied by each other, which is 101.4, or roughly 101 newtons. Okay, now there's a couple of important things here. First of all, sines and cosines, trig functions in general, are dimensionless. So there's no unit that goes along with them. So whatever unit comes over with your force is going to come through onto the whatever else you're solving for. The next thing is, when you write your answer, you have to write it in this form. P is equal to 101 and then the units, because the units are half of the answer. So that becomes really important. The next thing is, you really don't have to go through all these steps and write everything out. In other words, your calculator, of course, will just hold that for you. So instead of doing all the steps, I could just say sine of 25 equals divided by sine of 30 equals, and then multiply that by 120, and I would get the answer of 101.4, or basically 101. Okay. All right, so do you guys have any questions about that? Okay, the next thing is, I want for you, no matter what your problem says, solve all the problems using trig and algebra. In other words, you want to do an analytic solution, okay? There is, some of the problems tell you to solve it geometrically, which means you draw things like you could draw these two tip to tail like this, and then you could determine what it would look like for this to be vertical. The problem with that is it doesn't go anywhere. It does not lend itself to the basis of solving a three-dimensional problem. So it's interesting, and some people like to do it, and it's kind of fun. But ultimately, this is, Ernie's going to point right here. This is Ernie, my spokesmodel. Kind of looks like a pirate. But anyway, Ernie says, use this method. This is the one that's going to get you through to the next piece, okay? And have you ready for working on the next stuff. All right. Oh no, yeah, I do want to introduce this right now. Okay, the last thing I want to introduce is when we talk about components of forces or breaking a force into a component. Let's go back to our force here. This is the first one that we did. We have a 45-pound force acting 35 degrees from the horizontal. We said the X component is 36.9 pounds and the Y component is 25.8 pounds. There's a couple of different ways you can write this. If we want to say that force in calculus, you probably wrote it like this, where the X component would be 36.9 pounds, followed by a comma, and then 25.8 pounds. Something like this, okay? And that's fine. It's a good method. In vector mechanics and engineering, we tend to assign the X direction a unit vector called I, and the Y direction a unit vector called J. And then if we have that Z direction, we assign a unit vector called K. So what that means is, and unit vectors mean a lot more, but for now, it's just an alternate way of writing this, which we could say that force is equal to 36.9 pounds I plus 25.8 pounds J, okay? And so this is just in unit vector notation, and this is in, there's a name for it. It's not coming to me right now. So anyway, X, I, yep. And Y is J. Yep. K. Yep. Yep. Good question. And the XY or the IJK format comes in really handy when you start doing anything that involves the right-hand rule or the multiplication of vectors. It's a really handy way to do that without kind of having to redo your work a couple of different times. So it's handy to use, and it's introduced in section 2.2, I think. So just so that you know, but for this and the unit vectors, like I said, they really do mean a lot more than this. But at this point, that's all we have to know, is that you could just write that in either of those two alternative forms. Okay. All right. So you guys have any questions as you get started on your adventures with vector mechanics? Okay. All right. So we will meet again next Monday, which is February 5th. Yes. And if you have any questions between now and then, I am available. I'm not going anywhere this week at all. So if you need me, either schedule a Calendly appointment or stop by my office, and or you can text me. So when you start getting going on your homework, do give yourself time, because it will be quite lengthy. The chapter 2 homework will take a while. So make sure that you're ready to go. I think it's the 6th. I think it's next Tuesday. Yeah, let's double check here. So, but yeah, so when you get that turned in, we'll be good to go.